What's up, guys? We are back with another live stream. This is part 10 of Leetcoding until I'm a Leetcode god. Eating some watermelon. I'm not gonna lie to you guys. I really did not want to live stream today. I feel like I woke up feeling pretty depressed. But I need to hold myself accountable. I know that this is something I really want to get good at. And getting good at it means forcing myself to do it, even when I don't feel like doing it. You know? So I'm not going to guarantee that this is going to be a very long session of studying, you know? But I will say I'm going to put in effort and at least, you know, do something. I think even doing a small amount of Leetcode is better than just doing nothing. So yeah, I think I'm just going to warm up by doing some of the binary tree questions that I had done yesterday. Let's see. Let's say it was 27th. So I did invert binary tree. Let's do that. That's 2024. Invert binary tree. It's gonna be the 5th time I did this. Yep. How do I do this? Okay. So, if not node or if not root, just return none. I'm gonna look at root dot right. I'm gonna put it in a temp variable. Maybe temp equals root dot right. Root dot right is going to equal root dot right is going to equal root dot left, and then root dot left. Oh my gosh, bro, I can't get used to this keyboard. Equals temp. Yeah, so I'm just gonna swap the left and the right values, and then we're just gonna call the function recursively on those same nodes. Then we just want to return a root, right? Woohoo! Let's do balanced binary tree. Bro, this is the 28th. Why am I doing this? What are we gonna do? Balanced binary tree. This is gonna be the 4th time I've done it. No, don't look. Yeah, I mean, let's see. Right, so I feel so bad. My dog has like I think an ear infection, and he gets the same. He gets an infection in the same ear. It's always his left ear. Bro, I swear he'll get it. I have medication that I give him, right, for the ear infections, and I'll give it to him for a few days. It will work, but I swear, like 2 weeks later, 3 weeks later, he starts scratching that same ear. It's honestly at the point where I think I'm gonna take him to the vet. And bro, I hate going to the vet because I already know they just tax over there, bro. So I just gave him some medication. Hopefully he feels a little bit better. So what do I have to do again? What is this question? It's height balanced. Never differs more than one. Yeah, so I think the way that I solved this problem last time is I basically did like I created a function that basically determines if the binary tree, if two like trees are the same. I think I did like so. Okay, PQ, and I looked at like checking. I think writing comments for this helps me a lot. Check if both nodes are null. So if not P and not Q, return true. Actually, hold on. Actually, this is not. I'm thinking of the subtree question. For this. It was confusing questions. All we have to do is we have to check yeah, so we have to check. We're basically going to keep going down the binary tree, right? We're going to get like the left and right nodes. We're just going to keep going down. And if we get to a node that's null, we're going to return 0. Right? And then this is just going to get the depth, right? And then we're going to want to do is we're going to want to do like a DFS. Do we actually have to do DFS? Let's do if is balanced. me see. What did I even do, bro? Did I not do this? Oh my gosh. I'm being so dumb, bro. Keep forgetting. I got to... Yeah. That's why, man. That's why. Oh, dang. I also think I made a mistake before. I think I had is balanced right here. Should not have been that. Okay. I just not in that properly. I mean, I'll still put it here. I feel like I still need to remember that. I get the logic though. Let's do same tree. I feel like some of these binary tree questions are not, that are listed as easy, aren't really easy. Honestly. What do you want to do? Same tree. Seems the fourth time I've done it. Texting somebody. Bro, I was watching the Celtics game last night. They just made the NBA Finals. And honestly, like, I think I'm just gonna stay off Twitter until the finals actually happen, because I'm seeing a lot of toxic NBA discourse right now, and it's really nasty, man. Especially on the Celtics. I'm a Celtics fan, bro. I'll always be a Celtics fan. I'm a Celtics fan before anything. But listening to all these media, these sports analysts, talk about my team, it really seems like we're in a position where we can't, like, anything we do, it's just gonna be deemed as like not enough, you know? It really is just, we have to win the chip. That's why I'm not going to even go onto Twitter until the finals. Like, I may not even be on Twitter until like the result of the finals, because it's just nasty, man. We win we only lose 2 games throughout the whole throughout our whole playoff run to the finals. And people are like, well, you shouldn't have been in like close games with the Pacers. Let's say we weren't in close games. Let's say we were blowing the Pacers out. Well, it's the Pacers. And then they would be saying, wow, it's just the Pacers, but you're supposed to be blowing them out, which is true. But then they would start talking about us being battle tested. Oh, their clutch offense isn't that great, da da da. And I'm like, bro, what do you want? It's just so annoying. At the end of the day, like, I don't really want to engage in any more playoff talk until the finals, you know? I really don't want to hear it. It's just kind of exhausting having the same conversations, you know? It's like all of these questions we're having won't really be answered until the finals take place, so. Same tree. Given the roots of 2 binary trees, P and Q, write a function to check if they are the same or not. They're structurally identical. So we can write like if both nodes are null, right? That basically means if both nodes are null, that basically means we got to a point where we've like checked over all the other nodes, you know, and haven't ran into any issues. So if not P and not Q, we're gonna return true, right? Now if one node is null, that basically means like we're gonna be encountering example 2, in which case we can just return false. And then the only other case that I can think of is if the values are not the same, right? Because this is checking the structure. Now, if the values at the nodes are not the same, then we have to return false. If right, and then now I think we just want to recursively call this function on like both the left and the right side. Oh man. I'm back on Twitter. I still want to work out, but we'll see. We'll see what happens. I need to get better with recursion. I'm hoping that doing like recursion with binary search trees is pretty simple to me, right? Well, not simple, but it makes sense at least. I feel like doing recursion when we're not talking about, when we're not dealing with binary search trees, it's a lot more difficult. Yeah, I feel like I got ingrown hair. So annoying. Yeah, so a subtree, a binary tree is a tree that consists of a node. At any point, there's like a subtree. This question, there's no way this should be an easy. If I'm being honest, there's no way. This is a medium question. There's no way this is easy. You have to use another easy question in the solution. Let's just go through it again. I'm honestly just coding this from memory right now. Right, and then now I'm pretty much just gonna do DFS, and each time I pop something from our stack, from the stack, we're gonna just run this function on it to compare it. So we're gonna be every like child node we're looking at, just gonna compare that. I want to pop the most recent one. Yeah, man. subroot. If this is true, honestly, if it's false, then if not, then we want to return true. All right, no, we want to turn false. If we get turn true. So if it's just if there's none, wait, what do we want to do? Are we guaranteed to have a node? Okay, we're guaranteed to have a node. Actually, I think if, okay, yeah, I should be returning true. I should be returning false. Confuse myself. Need some watermelon. But one thing I hate about the summer in Boston, it's not even like the heat, bro. It's the humidity. I don't mind the temperature in my room right now, but it is so humid. It's actually scary. the third time I did that question. Medium. I only have a met on trees. I think I really started like Sunday. Maybe Saturday. I think Saturday is when I started. Damn, do I think that I can get through these? I want to do a new problem that I haven't seen before, just so I can increase like the what the hell? Like look. Look at, I've only done 87 problems, and like this has been the same since last week, since I've already done all of these. I just forgot, like I did these like 2-3 months ago, and I forgot all about binary trees, to be honest. Honestly, I might watch it after I do a few videos about binary trees. I mean, after I do a few problems, I might watch a video. Part of me feels like I need to yeah, look at this. Look at May, bro. I'm going in. And I was I Leetcoding here? Actually no, it wasn't. I'm going crazy in the month of May. I kind of want to do. I see people on like TikTok and YouTube, bro. They'll Leetcode for a whole year, and it would just be like green, 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 green. And I'm just like, damn, bro. That's impressive. That's a flex. I want to start flexing my Leetcode numbers. Once I get through the Leetcode 150, I'm going to start doing challenges, because once I do all that, honestly, it's just going to be about me getting better at actually solving new problems that I do. That's what I'm going to work on. But I want to, strengthen my understanding of just like the core concepts and then go from there. Anyway, let's do this. Oh, don't feel like doing this. Given a binary search tree, find the lowest common ancestor node of two given nodes in the BST. It is defined by two nodes, P and Q, as the lowest node in T that has both Q and P as descendants. Descendant of itself. 2 and 4 is 2. Okay. So it's a medium, like this is a medium binary search tree question. So I really think I'm going to have to use DFS or BFS in some way here. And I'm thinking that it's a BFS question, because basically what we're going to want to do is, like in BFS, how you're looking at all the kids first, like all the children nodes first. So if you go 6, we're gonna add all the children to our list, right? Or to our queue. And then after that, we're gonna go here, add all the children to the queue, go here, there's no children. We're gonna go here, add the children, you know what I mean? Whereas DFS, it will go like we add it's 6, we'll add 2, go to 2, we'll add 6, we'll add 2 and 8, but then we'll go to 2, boom, go down, boom, boom, but then go down. Like, you don't look at the children first. I think BFS is gonna be boom, boom. Yeah, I actually think you're going to be going like, I mean, it depends on how you add them, but if you're at 6, you're gonna add the children, then you're going to go here because you're gonna be first in, first out. Yeah, so you're gonna be going here, and you're gonna be adding the children. Yeah. Anyway, so I think the point of this question, I think, is just to incorporate BFS, and you want to just look at the like when you add all the children, you're gonna look at the node, right, that we just came from. That's what I think. Because what about 5 and like 0? It would be 2, right? But then how would that work? First, I'm just going to start by incorporating or implementing a binary search. I mean, a BFS. Bro, I suck at doing DFS and BFS recursively. Like I always do it iteratively. It just makes so much more sense in that case. I don't think the runtime might be a little bit faster with recursive calls, but I know it takes up a lot more space. So I don't know. My fear is that I'm going to get good at incorporating like implementing BFS and DFS iteratively, and then when I have to do it, like I feel like, let's say I'm in an interview, they ask me a question, I'm like, boom, here's the answer. It's an iterative implementation of BFS, for example. My fear is that they'll ask me, okay, do it recursively, and I'm gonna be like, oh no, please. Should I keep all like for I in stack? That should actually be Q. So we want to check if both Q. So I think at some point we can just check if Q and P are both in the stack. Oh no, because we're not just returning. Uh, um, Sue left. Oh. I don't know, man. I don't think this is gonna work. Are we guaranteed to be a solution? Will exist, okay. Well, that didn't work. Let me see how I did it. Oh. Is there a way to do this with BFS? Damn. The solution looks way more complicated, bro. Look on YouTube. Man. Bro, don't judge my YouTube searches.
Earn a $10 salon reward certificate after one bath or groom at PetSmart.
Anything for you.
We are suppressed emotion!
Disney and Pixar's Inside Out 2, June 14th.
Welcome to June's Leetcode Challenge. Today's problem is lowest common ancestor of a binary tree. Given a binary tree, find the lowest common ancestor of the two given nodes in the tree. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T, the binary tree, that has both P and Q as descendants, where we allow a node to be a descendant of itself. Here we have a binary tree and we're given P of 5 and Q of 1. We can see that the lowest common ancestor is going to be 3 here.
Give me a second, man.
On the left side's 5 and the right side's going to be 1. So that's going to be the lowest ancestor. Now if we're given 5 and 4, here we can see 5 is going to be our lowest common ancestor because 5 itself can be an ancestor, and that's going to be the lowest node on side of our levels of binary tree. Now my first approach was to do a post-order traversal of the binary tree and find every single node starting from the node that equals P or Q and all the ancestors added into like a set. And what I did was unioned the set together and then retraversed the tree to find the lowest node where the node exists inside of our tree. But that did work, but it was kind of inefficient. A better way of doing it is to do a post-order traversal here using a recursive function. What we'll do is find 3 scenarios. Either the node itself on the...
Look at post order. Okay. 4, 5, 2. So you go 4, 5, 2. Oh, this is a question.
Today, I'd like to teach you post-order tree traversal. We'll skip the basics since they're covered in the previous 2 traversal videos. Post-order tree traversal is defined by the following 3 steps. First, we traverse the left subtree. Next, we traverse the right subtree. Finally, we visit the node. Let's jump right in, using the example from previous videos. Starting at F, we traverse the left subtree and move to B. Likewise, we traverse B's left subtree and end up at A. We attempt to visit A's left and right children, but since they're null, we'll proceed to print A. Back at B, we're ready to traverse its right subtree. Following the pattern, we'll travel D's left and right subtrees. We move back up the tree, printing D and B on the way.
A, C, E, D.
I'm sure you see the pattern now. Let's watch the algorithm play out.
Okay, I get it. I get it. What's I doing?
The left node is an ancestor of P or Q, and the right side is an ancestor of PQ. And if that's the case, then this node itself is the lowest common ancestor. As long as we do a post order, the first node that we find that's the case, that's going to be the answer. But there's 2 other scenarios. It could be that this node itself is the ancestor of P or Q, and on the right side, right here, is an ancestor of P or Q. If that's the case, then this is going to be the lowest common ancestor. And the other way as well, where this is a ancestor of P or Q, and the right side is an ancestor of P or Q. So those are the 3 scenarios that could happen. So okay, what we'll do then is write a depth for search. First, we're going to store our answer as nothing, and we'll write a function here, depth for search, passing in the node. Our base case is obviously if not node, we'll just return if false. And we want to traverse our tree post order, starting with the left side and the right side, to see if either one of these are going to be an ancestor P or Q. So left, we want to traverse the ancestor search node.left, and the right, we're going to traverse as well, right side. Now, what about this one right here that we're on, the current one? Well, the current one, basically, if this node itself is equal to P or Q, then it counts as an ancestor, right? So this would be whether the node is equal to P or node is equal to Q. Now, if our three scenarios, first, if left and right, that means that this node itself is the lowest common ancestor, or if the cur and right, or cur and left, if either of these conditions are true, then we want to make this node equal to the answer, and then we can just return. Otherwise, we're just going to return here whether any of these are true, because that if any of these are true, that means this is an ancestor. So if left or right or cur. Oops. Finally, let's call.
I don't like the solution at all. I kind of want to see if there's. I want to see how a solution would look like if using iterative. I guess maybe it just makes more sense to do it recursively. Because truthfully, I don't really want to waste time trying to implement it iteratively.
My name is Jim Henson, and I'm a
It's just going to be
puppeteer.
something that's not really...
If Jim was here, I just have to thank him.
Hey everyone, welcome back, and let's write some more Leetcode today. So today we're going to solve lowest common ancestor of a binary search tree. And if you recall, a while ago in a video I showed you guys this sheet of the 75 blind problems that have become pretty popular. And so this is basically a spreadsheet that I showed with an entire list of those problems, and I've actually ended up making videos for most of these problems so far. The video that we're doing today is actually going to be lowest common ancestor, one of the few problems that I haven't done yet. So I will be linking this sheet in the description if you do want to take a look, and I'll probably be trying to wrap up most of the problems in this list. I think one of the next ones that I'm going to be doing is Alien Dictionary, because I really like that problem. And once I've gotten this entire sheet of problems done, I'll probably be making a playlist for it. But for now, you can watch the videos that are currently available for this list of problems. So in this problem, we're given a binary search tree, and we are supposed to find the lowest common ancestor of two given input nodes in the binary search tree. And so the lowest common ancestor is basically defined as being the lowest node in the tree such that P and Q are descendants of this node, or P or Q happens to be equal to this node. So basically, what we're saying is 6 can technically be a descendant of itself. So for example, in this example, we're given P equals 2, Q equals 8. So we're going to start at the root, because the root is always going to be a common ancestor of every single node in the tree, right? That's just kind of basic, right? For this node and this node, of course, this is going to be always going to be. So we're going to start at the root, because the root is always going to be a common ancestor of every single node in the tree, right? That's just kind of basic, right? For this node and this node, of course, this is going to be a common ancestor. It's not necessarily the lowest common ancestor, but it is a common ancestor. So what we're going to see is P is less than 6. Therefore, it's going to be in the left subtree, and it actually happens to be a direct child of 6. 8 happens to be greater than 6, so it's going to go in the right subtree. So basically, if we went in the left subtree, 2, is 2 going to be a ancestor of 2 and 8? Of course not, right? 2 can't be an ancestor of the node 8 if it's in a different subtree. Similarly, 8 is not going to be a common ancestor of 2. So basically, if we look at this level, or if we keep going down, we're never going to find a common ancestor between 2 and 8. So the lowest one that we found ended up being 6. So we notice if there's a split between the nodes that P and Q are going at, if they're going in separate subtrees, where that split occurs is going to be the lowest common ancestor. So if I change this problem slightly and I gave P as 7 and Q as 9, we would once again start at the root, because we know this is going to be a common ancestor of these two nodes. And so now we're going to check, okay, 7 is greater than 6, right? And 9 is also greater than 6. So therefore, we don't need to search in separate subtrees. We can just go to the right subtree to look for both of these values. We know that this is not going to be the lowest common ancestor. This could potentially, though, be the lowest common ancestor. So now, once again, we're going to repeat that. We're going to say 7, that's going to be less than 8. So for a 7, we're going to have to look in the left subtree. 9 is greater than 8, so for that, we're going to have to look in the right subtree. So since this is where the split occurred, that means this is going...
1 second, I'll be right back. Someone is making bro, is my mic even turned on? Okay, yes it is. Somebody's making bacon, I think. Kind of sounded like there was a fire.
going to be the lowest common ancestor for this input. So we would return this node as the lowest common ancestor. So one last case is if we changed Q to be a 6. So once again, we would start at the root, right? Before we were checking if P and Q were both greater than 6, then we look in the right subtree. If they're both less than 6, then we look in the left subtree. If one of them is in the right subtree and one of them is in the left subtree, that's how we know this is the lowest common ancestor. But what about the last edge case where one of these nodes happens to be equal to the root node? In that case, this is potentially the lowest common ancestor. It's definitely a common ancestor of both of these, but now if we go lower, for sure none of the descendants of this node, nothing in the left subtree or in the right subtree is going to be an ancestor of this node itself, right? So basically, if we ever reach the node itself, for example, 6, then that's going to be the lowest common ancestor. So it's an ancestor of itself, and it's also an ancestor.
Let me try and implement it before I look at the solution. Oh shoot. So basically we want to check if Q, if root dot val is less than Q, like let's say P dot val is less than root dot val. And Q dot val. I mean, because technically or it could be the same thing except reverse. That basically means that we want to return root. We're supposed to return the root node. What's the other cases? If because okay, or is that not? If p dot val and if p dot val is greater than root, or if p dot val is less than root dot val and q dot val is less than root, then we want to traverse the left side. Bruh, I'm not about to type all this. If p dot val if p dot val is greater than root dot val and q dot val is greater than root dot val, self dot lowest just go root dot right p q. Then the only case I'm still thinking about is if, you know, if root dot val equals p dot val or root dot val equals q dot val, then what? Then what are we going to want to do? Then we want to return
of 7, which can be found down here, right? So this problem isn't too difficult once you can kind of understand that if there's
that one case, I don't know how to do it. Wait, like we want to
split between these two nodes, then that's going to be the LCA, the lowest common ancestor. And since we're doing it this way, we don't have to visit every single node in the entire tree. So the time complexity is not going to be big O of n, it's going to be log n, because we're only going to have to visit one node for every single level in the tree. So basically the time complexity is the height of the tree, which is usually going to be log n. And the memory complexity is just going to be big O of 1, because we're not really needing any data structures or anything like that. That being said, let's jump into the code now. So as I mentioned, we are going to start ourselves at the root node, and we're basically now it's never going to be null because greater than the root value or the current value that we're visiting, and in that case we would have to go down the right subtree. So since we're going down the right subtree, we can update our
That was the iterative solution. Let me look at it. So we're going to return root. If root.left or root.right. Shouldn't this be root.left.val? Oh, so you don't even need. So you can literally just do it using these two conditions. Oh, so I guess, yeah, that makes sense actually. It just clicked. Because if it's here. Wait, hold on. I just had it, wait. Yeah, because, okay. If both the left and right, if both P and Q are less than the root, that means we're going to have to look on this side, right? If P and Q are greater than the root, we're going to have to look on this side. Else, that means P or Q is equal to the root. Like either P is equal to the root or Q is equal to the root. In which case, that means that, like, let's say P is equal to the root and P is equal to the root and Q is like greater than the root. That still means that this will be the, okay. That makes sense, bro. That makes sense. So I literally don't even need this. I don't need to. So I have to return this. Boom, 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 boom. Let's return this. Okay, that problem is not that bad. When was the last time I did this? It was... I've done this twice. Yeah, so this is my third. All right. I think, I don't know. I don't really have any notes here. I think it's pretty straightforward. I think if I just do it a few more times, I'll reach an understanding. I feel like I have to go over some, I feel like I have to go over some of the greedy problems again. Because greedy problems, I genuinely feel like you have to just practice a bunch of times. Or else you can just forget them. What's the next problem? Level order traversal. I feel like I should probably start taking notes on specific questions. Just writing it down. I have like a whiteboard right in front of me that I never really use. Like a level order. I have a habit of just like learning as I go.
Lowe's knows every color is the right color if it's from the brands you trust. Shop our Spring Into
I
Deals
have to find
event
a
to save
way
on select
to
exterior
make,
paint and
like-
stain. Whether it's for your home or job site, we've got it all so you can paint.
Today we'll look at the last variation.
Whoa. I need to find a way to make like my background blurry on OBS. I didn't really do much researching into it. But yeah.
Of tree traversal, level order. Level order differs from our previous traversals in that it resembles breadth first rather than depth first search. We've said before that breadth first makes use of a queue rather than a stack. Today you'll see how. In our depth first videos, we relied on the call
So is
stack for our
level order traversal just BFS.
recursive algorithms. We'll use an iterative approach for level order. Let's look at an example together. We'll print our output in the top left. Let's start with the pseudocode and walk through it line by line. First, we start with an empty queue. Let's add one node, the root of the tree. We're going to loop until our queue is empty. We enter the while loop, dequeue a node, and print its value. Finally, we add the left and right children if they exist. Let's look at an example together. We'll print our output in the top left corner and keep track of our queue data structure in the top right, with the leftmost element being the first to leave the queue. Following our pseudocode, we start with an empty queue. Next, we're ready to add the root of the tree, f, to our queue. Let's take f out of the queue and print its value. Next, we'll add its left child, b, followed by its right child, g, to the queue. We finish one iteration of the loop, and we're ready to dequeue another node. Consulting our queue, we see it's b. We remove b from the queue and print it. We add b's children, a and d, to our queue. We're ready to dequeue another element, this time g. We'll first remove g, then attempt to add its children. However, we only find a right child, I. We add b's children, a and d, to our queue. We're ready to dequeue another element, this time g. We'll first remove g, then attempt to...
Okay, I think I got it. I mean, So pretty much I'm just going to Q.append. Yeah, so I'm just going to keep appending, like, I'm going to keep appending, like, the children nodes, right? Because we're at 3. Yeah, 15, 17, yeah. So I believe this is what I should be doing. Okay, here, add 9 and 20 to the queue, right? We want to add that to, yeah, so I think we should be doing it here. Res. I think that we should clear that. We should do this every time we pop. I think that's it. Am I still in the while loop? No. Oh my goodness. Q dot left. Q dot left. Q dot right. Q dot append. Q dot left. Oh my gosh. Q dot append. Q dot. Oh my goodness. They're just the values. Oh, whoops. Oh my god. This is not gonna work. Boom. What? Dang, how did I do it last time? This is the same way I did it. Do I have to do that? Try this. Nope, still the same issue. Pretty sure this problem I did end up getting by myself though. Like the last time I tried doing it. Don't really know why this isn't working. I feel like I'm doing the same thing here. Oh, just gotta do it. I gotta have this here. Not here. That makes sense. What? Why does it add another one? Okay. So this has to be under the while loop, but not the for loop. My thing is, why wouldn't... What? Okay, yeah. See, I was expecting this to happen, which it does. That makes sense. What's the solution on it?
The search for your next where to starts here. Whether you travel to feed your inner foodie or their curiosity. Chase card members find more at chasetravel.com.
Let's go now, it's time to get busy. Let's go now, it's time to get busy. Come on, let's go now, it's time to get busy.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve binary tree level order traversal. It's basically just like it sounds, so we're given a for the result, and we also remember this queue with is, since the queue is non-empty, values that every single one of those value nodes from that in this queue currently. So for queue length, I'm gonna pop nodes from the left of the queue, right? First in, first out. And it's technically possible that the node could be null, so I'm going to have a check to make sure it's not null. Then we're going to take the node value and append it to the list level. And don't forget, this is also important that to our queue, we make sure to add the children of this node. So node.left and node.right. Technically, these could be null, but that's why we have this if statement. So then when the next loop comes around, right, we come around to the next iteration of the while loop, it'll make sure to check that these nodes are non-null before adding them to its own level list. Okay, so now we have
I feel like that's exactly what I'm doing.
have the loop in place that's going to iterate through every node of a single level. After we've done that entire level, what we're going to do is take our result and make sure we add every single level to that result, right? And then we're going to keep running this out.
Level.append node.value.
Outside while loop, the outer while loop, until there are no nodes left in our queue. That's how we know we've gone through every single level, added it to the result, and then at the end we can finally return the result. And one last thing we want to do is make sure that if we're adding a level to the result, we want to make sure that level is non-empty, because we know technically our queue could have null nodes. We're not.
Bro, is this not the same exact thing? Outside of it, yeah. Let's see. Hater. Maybe I really just have to do I guess we could just do like if Q, if it's a node. Bro, like, why? Oh, we have to do it in weights equals length of queue. Yeah, so node equals pop left. That's what I'm doing. If node. Yep, Q. Maybe it has to be this. I don't think it would make a difference though. If not level. Like, what the hell? I'm going a little crazy. Because why is this doing that? Get up, pop. Let's look at this side by side, bro. No joke. Because, hold up. Q equals... Yeah. Q dot left, Q dot right. Like what? Hello? He's alright, he was just making some breakfast. Yeah. Alright. Bye. Maybe I just can't. Would having this be here? Do that. Ah! Why is this doing that? Q dot pop. I feel like this is the same exact.
Queue is non-empty, we're going to get the length of the queue, right? So we're going to get the number of nodes or values that are in this queue currently, and we're going to loop through every single one of those values. This queue length is basically ensuring that we iterate through one level at a time. We're going through one level at a time. And with those nodes from that level, we're going to be adding them currently. So for queue length, I'm going to
I don't think this would change anything though. Bro, what? It really does. Wait, why does that make a difference though? Wait, why does that make a difference? So is it because for I range like the Q. So for the Q is gonna have one thing in it, right? Which is for I in Q. Let me do for I and Q. I want to see what it prints out. And then I just want to break after this for loop. So, okay, I think I see what I was doing. Oops, 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 oops. I see. So I think it's I'm sorry, I have to just like do some sanity checks. Okay. I see. So that's my fault. I was confused about how like for I in list works. I didn't think that it would do that. I thought it would just take this as just one element. That's actually good to know. I'm glad I went over that. It's actually very good to know. Okay, I'm gonna add that there. It's only the second time I've done this. Let me look at the next question. Damn, how long have I been streaming? Almost 2.5 hours. I spent a long time on that question. I could have just kept it pushing. What do I want to do here? I've solved this one. I solved this. March. Given the root of a binary tree Imagine yourself standing on the right side of it. Return the value of the node you can see ordered from top to bottom. Return the values of the nodes you can see ordered from top to bottom. 1, 3, 4. So just down the right side. I think that you just have to. I think we have to use DFS in this question. So we're going to need to do we're going to need to look at for pop the element off. We're going to so we only want to add the right nodes, but like, so you want to look if it has a right node, we're going to add that. And then Let me see. Is that it? Let me try. Wow. Look at that. I don't think it's going to pass all the test cases, though. Yeah. That's 158, though. Is it BFS? Why'd I think it was DFS? I'll try this. I'm just gonna just keep. Can I replace? Not replace. It's whatever, man. It's whatever. I gotta do everything myself. Oh my goodness. Same issue. What do I do? That's all we had to do. Bro, what am I even doing? Oh, yeah. Bro, maybe that was the issue in the first place. Low-key. I still don't think it would work though. This is my second time doing it. I'm actually gonna watch this. Let me just read a solution.
The Infinity QX60 was clearly designed to make an impression, and my first impression is, wow.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve binary tree right side view. The problem is pretty self-explanatory. We're given a binary tree, and basically imagine you're standing on the right side of it. So this is the tree. Imagine we have a person standing over here, right? You can see from the right side, you can see everything on the right side. And so what nodes can this person see? Well, they can see the root node, right? There's nothing blocking that. They can see this node. Can they see 2? Well, you can't really see 2 because it's behind this node, right? It's basically blocking this node, right? And the same thing with these 2 nodes, right? We can see 4 because it's the rightmost, right? Like, imagine the person sees this, but you can't really see that because it's being blocked by the 4. So when you just look at this example, this problem seems really easy, right? So your first thought might just be, okay, start at the root and keep going to the right? Just keep going down and we'll get the right side view, right? Every node on the right side. But we can make a counterexample pretty easily to show that that actually won't always work. Imagine this node 5 had a left child, right? Like let's say it has 7 over here. Now you can see that our result is going to be 1, 3, 4. We can't include these nodes because they're being blocked, but there's nothing over here, right? The 7 is not being blocked. So if this was our input tree, then our output would be 1, 3, 4, and we'd have to add a 7 to that because look at our person. They can technically see down here. So basically what this means is we can't only look at the right children, right? So you can actually solve this problem with a breadth first search. I know most tree problems you can just do depth first search, but this problem can actually be solved with breadth first search. There actually is a depth first search solution, but I'm going to explain the breadth first search solution to you because in some ways it's easier. And you might know breadth first search in a tree is also known as level order traversal. So it's also known as level order traversal, which you're going to see why it's called that just about now. So instead of saying that there's a person over here that can see only the right side of the tree, another way of framing this problem is saying, okay, for each level, right, each level of the tree, we want the rightmost node. So the first level, it's pretty easy because there's only 1 node. So we'll just take the 1 from that. What about this level, right? We look at the nodes together. For this level, we want the rightmost, so we get the 3. Next, we want the third level, and what's the rightmost value? It's going to be the 4, right? And lastly, we take the last level, and there's only 1 node. It's 7, so we're going to get the 7. So with a picture, this is pretty obvious.
So we're gonna put left. Anytime you're popping, it's gonna be the rightmost. Or actually, no, it's gonna be leftmost. What am I talking about?
Right? It's really easy to know what we're doing with a picture, but actually writing the code for level order traversal is a little bit tricky, and I'm going to show you how to do that. Basically, how we're going to implement this is with a queue data structure. So initially, what we're going to do is add the root node to our queue. So we're going to add 1 to our queue, and we're also going to have a result array. So now what we're going to do is take a look at our rightmost value in the queue. It's 1, so we're going to add 1 to our result. Next, now we're no longer looking at this node, we are looking at its children, basically the next level. So we can get that by taking the left and right child and adding them to our queue and removing the leftmost value from our queue. So we add the 2 and the 3 to the queue, and it's important that we do it in order, right? The left and right, the left has to be added first and then the right, because we always want to get the rightmost value when we add to our result. So now this is the second level of our tree, right? So what are we going to do? Again, we're just going to take the rightmost value. In this case, it's 3, add it to our result. And next, what we're going to do is we're going to look at the leftmost value, pop it, right? But before we pop it, we want to take its children. Notice it doesn't have a left child, right? That's null. And the right child is 5. So we're going to...
I think... Yeah, because at the end of this for loop, we're going to be at the rightmost, like, child, I guess. Makes sense.
Take its children and add them to the queue. So now we're adding 5 to the queue. So we're done with 2. Next, we have to remove 3 from our queue because we're done with this level. We want to look at the next level. So we remove 3. But before we remove 3, we have to add its left and right child. Notice it doesn't have a left child, but it has a right child, 4. So we're going to add 4 to our queue. So now look at our queue. We have 2 elements, and these 2 elements represent the 3rd level. So what we're going to do now is take the rightmost value once again in our queue and add it to our result because that's the rightmost value in this level of the tree. And now we're going to repeat that process. So for 5, we're done looking at 5, but we have to look at its left and right child. It has one child, 7. So we remove 5 and we add 7 to our queue. And we also look at 4. So we're done looking at 4, right? So we pop it, but before we pop it, we want to look at its children. Notice both of the children are null. So basically we've reached our base case. We don't end up adding more elements to the queue in this case. And now there's only a single element remaining in our queue, and that element represents the 4th level of our tree, and the rightmost node in that level is 7. So we can add 7 to our result, and we know we still have to remove 7 now, right? So remove 7 from our queue. Notice it didn't have any children, right? Both of the children were into code. So I'm going to initialize a empty null. So I'm going to hand current length.
What is the advantages to using the actual like DQ versus like just a normal list? Just do this is gonna be the last problem I do. This is my second time doing it. me see what my friend BG has been doing. BG, bro, you gotta grind, man. Last time you did a problem was like a month ago. It'd be like that sometimes. Okay, what is count good nodes in binary tree? What else? Validate binary tree, tree, K small element, and BST. You're gonna have to probably use a heap here. Given a binary tree root, a node X in the tree is named good. If in the path from root to X there are no nodes with a value greater than X. Root node X in the tree is named good. If in the path to X there are no nodes with a value greater than X. He's always a good node. Five, 3, 4, 5 is the maximum in the value path. Yeah. So there's 3 different paths. So you could do like 1, 2, okay, like 4, boom, 3, and then what, 3? Do we count like 1? So we're always guaranteed a node. Okay. How can I do this? Can I use DFS? I think so. I think I have to use DFS. I think what we can do is we can just look at like the way I'm thinking about it is we can, like, if we're at the root, we can look at whether or not the left and right nodes, child nodes, are greater than the root, or greater than damn, how did I guess it's not really the root, but will have to be greater than each value. Would you have to like try every path with like comparing each value? So like 3. Man, I don't even know. I actually don't know how to do this question. I thought I did. I solved this already? How did I do this? Damn, bro, it's hot in my room all of a sudden. Okay, so I knew you had to use DFS. Honestly, bro, I might call it here. Because I'm pretty hungry. I'm going to do this problem myself. And then tomorrow I will just start from like here. And then do these 3. But yeah, I'm honestly very hungry. And I have other work that I have to do. So, thank you for tuning in. Part 11 tomorrow, of course. Actually, I probably won't have part 11 tomorrow. I'm gonna have to be somewhere pretty much all day. If I come back tomorrow at a decent time, then I'll do it. But if not, then all right. Let's stop the stream for now. Thank you guys for your support. I know there will be a point where I'm getting at least 2 viewers or something, bro. 'Cause right now it's just me. Okay. Thanks.